Hi everyone. As you can see, I'm in a Zoom setup today. Because what I want to try is the AoPS practice AMC10. There's also a practice AMC12, but in this video, we'll be doing the practice AMC10. Well, so why am I in a Zoom video is because this is a timed practice, and it is a pretty good time practice. So I would suggest that for those of you who are, well, haven't done the AoPS practice yet, you can either follow along with me in this video or you can try it on your own at the link in the description below. It's a timed 75-minute practice, which means that if I were to use my usual setup, it would involve extracting out the questions and then writing out my solutions, but that would take a bit too much of the 75 minutes to do. So I'm going to do it live, and that will probably entail, if it goes according to what I am predicting, it will involve me annotating all over the screen, because the questions are, of course, going to be online. Now, for those of you who are taking the AMC online, you would certainly have a similar interface, but you will be doing your workings on paper. I don't think you would be annotating on your screen very much. Okay, so let's click start. Is there an extra screen? I think there's extra screen. Okay, so students have 75 minutes. Double check that your computer is set to stay awake for the duration. So it's currently about 10 p.m. local time. I've had a few lessons before this, so I'm trying to stay awake, but I think my computer should be fine. So let's click continue and we shall begin. No, we have not begun. Rules. Okay, so these are actual rules as far as I know. You're allowed writing materials, rulers, compasses, and erasers, and blank paper. A computer with one browser tab open. Okay, let me close that. I don't think I need that. No calculators and no other tools, including protractors and graph paper. I certainly don't have that for my screen here. All right, so I don't know how the questions are going to look. Some of you have seen my recording of the practice competition from a couple of years ago, but this is different. Every year has a fresh set of problems. So let's see how it goes. Okay, so let's start. Yes, I do want to start. And let's see how this looks like. Now, I think for the first few, I'm just going to talk it out loud. Joe harvested 48 acres in 14 hours. How many did he harvest after 8 hours? Okay, that is surprisingly annoying for question 1. Computationally, 48 times 4 over 7 is 192/7. That is 27 and 3/7. And 3/7 is 0.428571. So it should be option D. Now, it shows your answers being saved like this. I believe that the platform for the actual AMC will look something like this. Question 2. Okay, this is computational with parentheses, so we just go from inside to outside. So 2, I'll just call this hash 3. It's not really a hash. 2 hash 3 is 2 plus 6 minus 1 is 7. 0 hash 7. Oh, actually, I should have done 0 first because that just becomes minus 1. So 2 hash minus 1 is 2 minus 2 minus 1. So -1 should be the answer. Question 3. The sum of 3 numbers is 71. The first number is both 13 more than the second number and 3 times the third number. This feels like a very familiar kind of question. Okay, let's use the third number is x. The first number is 3x. The second number is 3x minus 13. 7x minus 13 is 71. X is 12. 3x is 36. 12 times 36 is equal to 432. I'll just circle it, right? Forget that I'm an online platform. So be it is. Yeah, and I forget that I need to erase my annotations every time. Question 4. Two fair 4-sided dice and 1 fair 8-sided die are rolled. What's the probability that the sum of the results of the 2 4-sided dice is greater than the result of the 8-sided dice? You know, I don't seem to find a simple way to do this, but I feel like as if I can just do this manually. So manually would mean that for the 8-sided die, there are 1, 2, 3, 4, 5, 6, 7, 8 with the same probability. I forgot to write 8. They're all 1/8. Whereas for the sum of the two 4-sided dice, my outcomes are from 2 to 8. There are a total of 16 outcomes, of which the number of ways goes 1, 2, 3, 4, 3, 2, 1. And so what's the probability that the sum is greater? I'll ignore the 16 and the 8, right? So it's 1 over 1 to 8. 1 times 1, 2 times 2, 3 times 3, 4 times 4, and then 3 times 5, 2 times 6, 1 times 7. So this sums to 1 times 8, 2 times 8, 3 times 8. So that is 48 plus 16 is 64. I have that right? Seems very coincidental. Well, don't see anything wrong with this. So I shall take it as it is really just exactly 1/2. Which is interesting. Now this is live. I may be doing something wrong and you can shout at me through your screen. You are very entitled to shout at me through your screen. Okay, question 5. The unit circle centered at C and the isosceles right-angled triangle intersect. The shaded region and the region outside have equal areas. What's the length AC? Okay, so this is 45 degrees. The shaded area, therefore, is 1/8 of a circle, 1/8 pi. Now, that means that the triangle has area 1/4 pi. If I complete it like that, that means that the area is 1/2 pi and AC is just the square root of 1/2 pi. Square root of 1/2 pi looks like that is option D. Question 6. Qian drives 5 miles northeast, then 15 miles. Yeah, so this looks like Pythagoras already, except that instead of north, south, east, west, we are using the, I don't know if there's a name for the other 4 directions. There's probably a name. Let's just draw a compass. So 5 miles northeast, then 15 miles southeast, then 25 miles southwest, and then 35 miles northwest, and then 20 miles northeast. Now, because all of these are right angles, I want to kind of tilt my head and say that this 5, 20, and 25 means that it just kind of balances out here. And this distance is just going to be 35 minus 15 equals to 20. So my answer is 20. Yeah, I realize one drawback of this is I can't check my workings because I'm erasing them. For those of you who are taking the contest online, I would suggest that on your piece of paper, just divide the piece of paper into like 4 sections for 1, 2, 3, 4, or 6 sections for 1, 2, 3, 4, 5, 6, and so on, just so that you can find back your workings if you want to check or if you got stuck halfway. Okay. Question 7. Square PQRS has side length 2. This feels a little bit harder than a usual start of an AMC10 paper, I have to say. But anyway, it should not be too bad, right? Okay, so I just want the distance of A to B. It should be fully symmetric. So essentially, I just want this distance AB. This length here are 1 because by symmetry, this is the center of the circle. this is 1, 2, and square root 3. So the sides of this equilateral triangle are 1 plus root 3. This length becomes 1 plus root 3 times square root 2. So that is option B. Actually, that was not so bad as I thought it might be. Question 8. How many of the integers from 1 to 100 equal p times q squared, where p and q are distinct prime numbers? So I definitely need to list out some prime numbers here. How many do I need to list out? Okay, so if q is 2, then 2 squared, p is at most 25. Okay, so I just need to list out primes up to here, and that's all I need to care about. So if q is 2, then p is at most 25. Remember, they are distinct prime numbers, so I must remember not to include 2 again. And I feel like I'm going to do this at some point in a later case. So I shall say it out loud to remind myself. So 2 squared, exclude 2, 3 to 23 means there are 8 possibilities. If q equals to 3, it means I'm up to 11. So 2, 5, 7, and 11, 4 cases. Q equals to 5, 2 cases. Q equals to 7, 49 can only be times 2. So 1 more case. That's all right. That's not too bad. That is only 15. Now, I can kind of tell you that I am not going to check my answers. So I may be actually done in less than the time allotted. I'm not going to check my answers. And that means that there may be some careless mistakes. And I hope to use that as a teaching example, just to demonstrate what kind of mistakes can happen. And maybe you're already shouting at me through the screen. I'm not purposely making mistakes, but at this speed and at 10 p.m., things do happen. Okay, question 9. I feel like I've said this question before for one of my SMO mock papers. How many 3-digit numbers have non-decreasing digits from left to right? Non-decreasing means that they can stay the same or they can go up. Okay, so there are 2 methods to do this. The first method would be to kind of just do a bit of listing, right? So I say that, okay, for the first digit, if it's 1, and then if the second digit is also 1, then I have 1 to 9. The second digit is 2, then I have 2 to 9, all the way until only 9. So how many cases are there? This is 1 plus 2 until 9 is 45. Now, if this is 2, then again, I can split into cases like this. And this will give me 1 to 8. So manually just adding the triangular numbers should work. And this should be equal to 165. Yeah, I just used the last digit to check. Now, another way that you can do this, which you should certainly not talk about alternative methods in a real AMC, but this is still a somewhat teaching video. So a bit of hubris. I don't know if I have actually enough time for the back. The alternative way you can do this is to actually say that you are just counting the number of ways to pick 3 digits from 1 to 9. And you can treat it as the number of ways to pick 3 digits from 1 to 9 in your usual stars and bars approach or your partitions approach, whichever thing you call it. It's like 3 identical balls into 9 boxes. And this is the same as the number of ways to arrange 3 objects with 8 partitions. So that would be 11 choose 3, which is also 165. Okay, so in this case, I've shown 2 methods. Please don't do 2 methods in an actual AMC. To check is fine, if you have time to check. Okay, question 10. Triangle ABC has a right angle at B. We draw altitude BD with length 4. The length of AD is shorter than the length of CD. If the area of ABC is 50/3, what is the length of CD? Okay, so, I mean, I can calculate AC. So AC is 25/3. Now, AD is the shorter one. CD is the longer one. So you can already eliminate this option here. Now, the property that we are going to use is the fact that these triangles are similar to each other. By these, I mean the two smaller triangles. ABD is similar to BCD. This is a classic nested right angled triangle configuration. So AD over BD equals to BD over CD. So AD times CD is BD squared, which is 16. And I can actually just use the options to check, right? If they sum up to 25/3, technically this would be a quadratic, but I can see that 16/3 times 3 does work. So I don't actually have to do the calculation. Answer is just 16/3. Yeah, and 3 is kind of the trick option, right? Because CD is the larger one. Okay, question 11. Corner is removed from a square of side length 15 inches to make an irregular pentagon as shown. This is actually a very nice. It's irregular, but it's nice. It was a square of 15 inches. Now it has an area of 195 square inches. Why do I feel like this is almost like the question that we just did? It's very peculiar. Also peculiar is the fact that I've literally already forgotten what the question is that we just did. I have no recollection what that is. What was it again? Never mind. We'll look at it later. So this area is 15 squared minus 195 is 30. We have lost 30 square inches of units. Now if I call this x and y, this is 15 minus x, this is 15 minus y, and this is root x squared plus y squared. What we have apparently gotten is that this totals up to 56. So x plus y minus root x squared plus y squared is apparently equals to 4. And also, I have that half xy is 30, so xy is 60. Okay, so what is the easiest way to do this? I think the easiest way to do this is to do a substitution for a is x plus y and b equals to xy. So a minus root a squared minus 2b is equal to 4. B is 60. So a squared minus 2b squared is exactly what I want, right? It means that if I actually divide, so this is quite clever, right? If I use the conjugate, these two multiply to a squared minus 2b equals to 120. So it means that this is 30. And so I just use this and subtract and divide by 2 to get 13. That's what I want, right? This is actually square root x squared plus y squared. Okay, so I didn't actually need to do that. I could have just used the conjugate straight away, but I felt that it looked a bit clearer to me in this version. I don't know why. Nevertheless, the answer is 13. Which is option B. Okay, what was the previous question? This one. I totally forgot what the question was already. Question 12. There are two kinds of blocks, red and blue. The red blocks are 2 inches by 2 inches, and the blue blocks are 3 inches by 2 inches. In how many ways can you place red or blue blocks together to form a 15 by 2 inch space? 2 inches is redundant, right? Because it's 15 by 2. It just means that you've got 2 and 3 summing up to 15. Yeah, that's redundant. So you can have 5 trees, or every pair of trees can be replaced by 3 twos. And that's your 3 possible combinations. My trees are basically the blue blocks. The twos are the red blocks. Now, this obviously is all 3 blocks, means there's just one way. This one is 6 choose 3. That's 20. And this is just 7 ways. So altogether, you get 28. I'm still fairly sure I will make at least one silly mistake at some point, just by sheer probability that tends to happen. But generally, things should be okay. Okay, this thing here. I'm thinking whether I want to pull out a trick. Yeah, let's just pull it out, right? So it's well known that your units digits will repeat after 4 steps for any number. When you just take powers, repeat after 4 steps. Doesn't mean it takes 4 steps, but it will repeat after 4 steps. So I can also say that, well, this 11 to 11 just has 1, so it doesn't contribute anything. And I can also merge together all of these trees into 3, 13, and 23. So 39 trees. What happened to my cursor? 3 to the 39 and 7 to the 7 plus 17 is 24. Now, what I'm saying is that every set of 4, it goes back to repeat and it goes back to 1. So 7 to the power of 24, if you write out the powers, indeed it goes 7, 9, 3, 1, and then loops back. So this is just 1. For 3, it's kind of the opposite. It goes 3, 9, 7, 1, and loops back. And 39 is 3 mod 4. So it will be 7 times 1. This is just 7. Okay, the sequencing is a bit weird, right? This doesn't feel like it is the hardest question we've done so far. Okay, question 14. Here's a quadrilateral. What's the distance from C to the midpoint of D and B? So that just means the midpoint of DB, right? Let's see here. Okay, this is weird, right? Now, this is weird because it looks like as if it's goading me to use the cosine rule. But the AMC10 does not usually need the cosine rule. So I'm going to try to stick to that for AMC10 video. We will use just the 30, 60, 90 triangle, which is, I think, considered sufficiently elementary for the AMC10. So the ratios are 1 is to root 3 is to 2, means that this is 3, this is 3 root 3, and this is also therefore going to be 3 root 3. That's nice because it means that this length here is going to be, well, by Pythagoras, it will just be, well, only Pythagoras, root 2 times of this is 3 root 6. So if I call this M, BM is 3 root 6 over 2, and CM, which is what I want, is the square root of BC squared minus BM squared. BC squared is 36 over 2 is 18. BM squared, 3 root 6 squared is 9 times 6 is 54. 54 over 4 is 13.5. So square root of 4.5. One of these options is that's square root 9 over 2. Yeah, so that's 3 over root 2. Question 15. How many obtuse, don't like this. How many obtuse triangles can you place on the 3 by 3 grid pictured below such that the vertices are on the grid? Okay, don't like this. I just want to get a ballpark, right? So how many choices are there? 9 choose 3 is 84. There are 84 choices. Now, a bunch of these, there are a total of 8 of them, which are straight lines. Okay, so I don't really like it, right? How do I do this efficiently? Yeah, I think I'm going to split into cases then, right? I am thinking of splitting into cases based on whether I use the center or I don't use the center. Now, if I don't use the center, I'm just taking a second to think of where are my obtuse triangles going to be. And I'm seeing that if I don't use the center rather, the only types of obtuse triangles can find are these sort. And of course, rotations, right? So unless I'm missing anything, which I may well be, it means that you would do something like for each of these edges, there are sort of 2 places where you can jump to that give you an obtuse triangle. And there are 1, 2, 3, 4, 5, 6, 7, 8 times 2. So 8 times 2 is 16 without the center. I'm using the American spelling of center since this is an AMC. Now, other side of it is if I do use the center, and if I do use the center, how do I get obtuse triangles? I feel like as if the way to get obtuse triangles is only like this. Which means that you pick one edge here. If I pick this one, then there are 2 choices opposite it, and then there will be 2 times 4 equals to 8 with the center. So that is a total of 24. I don't see anything that I'm missing. I may be missing something, but if I'm not missing anything, the answer should be 24. Question 16. I don't know if you're seeing me moving my own face around. It's a bit weird because this time block is also blocking some of my of the questions as well. Okay. Dartboard. 3 darts are thrown at the board so that they stick at 3 random locations on the board. What's the probability that each dart lands in a different region? I can just calculate the area of each region, right? Pi r squared. So 16 pi here. The big ring will be 36 pi minus 16 is 20 pi. I don't know about you, I always found that this ring doesn't look like it's actually bigger than the inside, but somehow it is. 8 pi, this is 64, minus 36 is 28 pi. I always found it a bit weird, intuitive. Maybe this is not to scale as well, but I always found that my estimation of areas of circles and this annulus is a bit off. Anyway, I don't actually need this. I'm basically saying that the regions, if I divide by 4 pi, it's 4 is to 5 is to 7. So what's the probability that each dot lands in a different region? It is, okay, I think it's easier if I just treat it as if that there are these 16 possibilities, right? Like 4 plus 5 plus 7 is 16. So as if it's 16 cubed, and my choices are that in a different region means that 4 times 5 times 7 times 3 factorial, because there are 3 different orderings. That surely has to be option B without doing much calculation, because that's the only thing that has a 5 and 7 left over. So I'm going to just trust that is correct and move on. Okay, question 17. What's this like FizzBuzz game, right? FizzBuzz is a very famous programming exercise or programming interview exercise. But this is multiples of 3 or has 3 as a digit. How many times do they say buzz? Okay, so it means that either multiple of 3 or has 3 as a digit. Let me think. Okay, I'm going to remove the 3 first. So from 1 to 1000, I'm going to count all the non-buzz. Now, first of all, if there are no 3s, it is basically like your 3-digit number. Your options are 0 to 9 excluding 3. So there are 9 cubed possibilities. One of these is 0, but there's 1000, right? So it balances out. There are 729 numbers with no 3s inside. Now, how many of these are multiples of 3? Okay, non-buzz means that so for this one, it's actually quite nice, because we realize that if you exclude 3, your digits are 0, 1, 2, 4, 5, 6, 7, 8, 9. So each of the residues mod 3 are represented 3 times. Now that means that for, let's say, this 3-digit number here, you are going to end up with exactly 1/3 of them will have the digit sum be a multiple of 3. Right? 1/3 of them is 2, 4, 3. Now, we also had already 271, because 1000 minus 729. So 271 and 243 adds up to 514. Oh yeah, because I replaced 0 by 1000, right? So I replaced 1000 by 0. 1000 is not bus, 0 is bus. So I've overcounted by 1. The correct answer is actually 513. So that makes sense. Okay. Question 18. This is very peculiar. I've just taught a lesson and I feel like I've just set a bunch of questions that look very similar to these. So it's all very strange to me. And I guess doing things quite a bit faster than would be normal because of this series of strange coincidences. Okay, so how many ordered triples of positive integers a, b, c are there such that a times b times c is 10 to the power of 10? This is 2 to the power of 10 times 5 to the power of 10. Now, basically, you are distributing the 2's and distributing the 5's. To distribute the 2's, you have 10 2's to distribute to 3 boxes, right? And this becomes like your stars and bars again. It will be 10 objects with 2 partitions, 12 choose 2 equals to 66. And then now it's just 66 squared. Now, every year when you're doing the AMCs, right, there'll always be some questions that are a bit misplaced. It's not deliberate, but it does happen. Sometimes it's just due to an oversight, like you didn't realize such a simple solution existed, or rather the question setter didn't realize. Sometimes it's because it is just your own personal preference. And also sometimes it's just that because there are 2 papers, the distribution is such that they wanted to have some nice ratio of all the types of problems, but they may have inadvertently got the difficulties a bit off. So do look at some of the later questions. They may not be actually very hard. Okay, question 19. This also looks like a very familiar question. And basically what I want to do is just to get some ratios. So I will draw this. Now I'm going to just assume that the small circles have radius 1. Since it's a ratio and I've not been given any lengths, so this is 1, this is 2, and once again, this would be a, well, if I chopped it into here, this would be a 30, 60, 90 triangle. This is 1, means that this length here is going to be 2 over root 3. So your big radius is 1 plus 2 over root 3. Sum of the areas of the 3 smaller circles, I don't need to write pi, so it will just be 3 over this thing squared, which explains all of the appearances of weird looking things. So we shall just simplify this a little bit. It's not going to be 3/4, we can say that much. Maybe I can multiply root 3 squared to the top and bottom, which means 9 over root 3 plus 2 squared. I think that's nicer. So 2 plus root 3, but 1 over 2 plus root 3 is 2 minus root 3. So this is just 9 times 2 minus root 3 squared, which is 7 minus 4 root 3. Okay, so that is clearly option A. That's better than I was expecting. Okay, question 20. 3 blue, 2 red, 1 green marble. How many unique sequences of every length of colors of marbles can someone withdraw from the bag without replacement? Again, pretty annoying. I'm thinking about whether there is a nice way to do this. I am not seeing one. And the fact that this is quite small just makes me tempted to just list. So I'm going to just list. It's probably a better way, isn't there? Don't see it. Never mind. I'll just list. So length, okay, the empty sequence. All right. Length 0, there's one way. Length 1, there's obviously 3 choices. Now, length 2, what I'll do for length 2 is I will say that there are just 3 times 3 cases except for green green. So there are 8 ways. Now, I will also go the other end. Length 6 is just going to be 6 factorial over 3 factorial, 2 factorial, 1 factorial, which is equal to 60. And I will also say that length 5 is the same, I think. Yeah, so length 5 is the same because if you take any length 5 sequences, the first 5 of every of these length 6 sequences rather will be different. So there will be another 60. Anyway, if I'm really wrong, right, the options are quite close together. So if I'm off by a lot, like let's say off by 30, it'll just be none of the above and I will be alerted. So it's the small ones that I'm concerned about. Now, length 3, I feel like there is no choice except to go with boring approach. So if there are there's 2 blue, 1 red, 2 blue, 1 green, you can have 2 red, 1 blue, 2 red, 1 green, and you can have 1 of each. You cannot have 2 green. So 1, 3, 3, 3, 3, 6. This totals up to 19. And then with length 4, which is also fairly annoying, but I can just take note of the distributions. If they have 2 different colors, you can have blue, 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 red, blue, 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 green. Or if I use 3 blue, I can do this. If I use 2 blue, I can have blue, blue, red, red, blue, blue, red, green. If I use 1 blue, then I have blue, red, red, green, and that's all. I could also consider which 2 to exclude. Yeah, that is probably a better idea, but I've done this already. So there are 4 ways, 4 choose 2, which is 6 ways, 4 factorial over 2, which is 12 ways, and also same thing here. So this sums up to 38. Now, moment of truth, if I get something in this range, I trust I'm correct. So this sums up to 12, 12, 60, 60, 132, 132 plus 57 is equal to 189. Okay, that's good. It's good because if I got the biggest option and I didn't overcount anything, I should be correct. Yeah, I'm going to have to erase all of this, right, which is mildly annoying. Okay, question 21. Unfair coin has sides, heads, and tails. Probability of flipping 5 heads in a row is at least the probability of flipping 4 heads and 1 tail in some order, but this is unfair coin. Okay. But the probability of flipping 6 heads in a row is at most the probability of flipping 5 heads and 1 tail in some order. Okay, so let's just let the probability here be P and 1 minus P. So 5 heads in a row, P to the 5 is at least 4 heads, 1 tail in some order. There are 5 orderings. But P to the 6 is at most 5, sorry, not 5, 6 P to the 5, 1 minus P. So this is begging me to cancel off P to the 4. Then begging me to cancel P to the 5. This tells me P is more than or equals to 5, 6. This one tells me that P is at most 6 sevenths. Okay. If you flip the coin the number of times such that you are guaranteed to have more than, this is a very weird sentence. You are guaranteed to have more than a 50% chance of flipping at least 1 tails. Okay, more than 50% chance of flipping at least 1 tails means that you have a less than 50% chance of all heads. And so it means that if you, the number of times, if I call this n, it's saying that P to the n is less than half. What is the lowest number of expected heads you can have? expected hits is Pn. Okay, so it's between 5, 6, and 6, 7. I think in AMC terms, I'm quite sure it will be one of these two things. So I'm just going to put in 5, 6, and 6, 7 and see how long does it take for me to basically what's n and what's Pn. If P is 5, 6, okay, 25 over 36, 125, 216, 625, 1296. Okay, so n is 4. And I get 10 over 3 for my Pn. That's promising. If P is 6, 7, then the next powers, I've already got my powers of 6 down. Okay, so it must be at least 5, right? Because this is I'm pretty sure 5 will work, but 5 times 6 over 7 is already 30 over 7. So which means that the minimum would be 24, sorry, would be 10 over 3, because you cannot get 24 over 7 since this is still more than half. So answer is option A. Question 22. Okay, all the digits are different. Thinking of, again, what clever methods are there? Now, I am seeing, of course, that the last digit is the same. So your options would normally be 0, 1, 5, and 6. It cannot be 0, otherwise there will be 0, 0, and they are supposed to be different. It cannot be 5 because then it will end in 25 for both of these, but YZ and WZ are different. So it's either Z is 1 or 6. Now, I'm also seeing that W and W repeat. So this kind of tells me that W is quite big. W is quite big because basically this is telling me that I've got W1000 by multiplying W0 by W0. So this is roughly saying 1000 W is around 10 W squared. Now, this tells you that W is around 10. Now, of course, this is just vague, but this suggests to me that W should be 9. So I'm just going to try 91 squared and 96 squared. 91 squared is 8. It's quite close to 8,100, right? So it's not even big enough. I need 96. 96 squared is 9216. So that does work, right? Okay, so that means that YXWZ, Y is 1. X is 2W, oh, so 1296. Oh, great. So that's 36 squared. And the answer is 3. Question 23. Random positive integers at most 2 to the 10. What's the probability that A minus B is some power of 2? This does not seem very hard. Clearly, it is the denominator is that there are 2 to the power of 20 choices. So we're just counting the number of pairs. The number of pairs for some integer k means that the difference can be 1, 2, 2 squared until 2 to the power of 9. I'm strongly suspecting that the answer is that something over 2 to the 19, because the 2 to the 20 would be if you forgot that you can swap the order. So I think it's probably something to the 19. In fact, it has to be, right? Because there must be an even number of ways to do it. So in fact, I can say that for sure already. E looks weird, but we'll see. So number of pairs, if they differ by 1, you have got 2 to the 10 minus 1. Then if they differ by 2, you get 2 to the 10 minus 2. Okay, I see where this is going. This is just like that. Over 2 to the 19, because these can all be reversed. And that is going to be 10 times 2 to the 10 minus the sum from 1 to 2 to the 9 is 2 to the 10 minus 1. So this is 9 times 2 to the 10 plus 1, which is 9217. Okay, so that's why that weird number down there. Okay, question 24. V be set of vertices of a regular dodecagon, which is a 12-sided polygon. Well, we know that. We can see that. How many vertices have vertices? How many triangles have vertices in V and contain the center of the dodecagon in the interior of the triangle, completely inside? That's interesting. And I am not sure. Options are quite small, right? So listing is always a possibility. Let's take a peek at 25. This doesn't look too bad. I think I'll do this first, right? This doesn't look too bad. So 7 by 8 rectangle has 4, 3, 4, 5 triangles drawn in below. Circle is inscribed to be tangent to the hypotenuses of the 4 triangles. What's the radius of the circle? Now, whenever I see something like radius of the circle, the reason why I say it's not so bad is that I'm thinking that I can just use some area argument. In fact, yeah, so if I mark the equal angles out, so it's not there, it tells me that these are right angles. So if I were to extend them out, like that, I get a nice kite. And that should be quite easy to compute the relevant length, right? Because this is 7 by 8 rectangle, so this is 1 and 1. This is similar to that. You should probably not use black for the ones, right? So this is 1 and this is 1. Now that just looks like I'm saying they're equal length, which is true, but I mean that they are 1. This here is equal to 4 over 3, which means that the whole hypotenuse of this big thing here is going to be 4 over 3 plus 7, which is 25 over 3. So that means that because this big triangle here is also a 3, 4, 5 triangle, it's also similar. So this length here is 20 over 3, and this is 15 over 3, this is 5. Well, we already knew that, right? But this just confirms it. And so I'm going to use the area of this big thing here. Area is 20 over 3 times 5, times half times 2. Now, when you have an inscribed circle, it means that your area equals to radius times semi-perimeter. And your semi-perimeter is just 20 over 3 plus 5. So my answer should be 100 over 3 divided by 35 over 3 is 20 over 7. So that would be option B, which is frankly a little bit disappointing as a question 25, right? It was not that hard. Now let's get back to 24, which I was a bit lazy to count just now. How do I do this? Okay, I'm going to just forcibly count those that include this vertex. So the number of triangles that include this vertex, and then I'm just going to kind of like draw a dotted line here just to remind myself that, okay, I cannot pick this one for sure because then it would already be on the line. Now, obviously, if I want to contain the thing in the triangle, the center in the triangle, it means I need to pick something from the left half and something from the right half. So I'll just say that if I pick this one, there is no way to include the center, right? Because it means that I need to have included something in this range which doesn't exist. So there is nothing here. If I pick this one, it means that I need to pick a point in this range, which there is one choice. If I pick from here, it means that I have got 2 choices and then 3 and then 4 choices. Yeah, so I have to use something here, which basically means I've just concluded that there are 10 triangles using this. Hey, that's not so bad. So there are 10 triangles using this, means that there are 10 triangles using every of the vertices. So your answer is just 10 times 12 over 3 equals to 40. Yeah, so that is what I think the answer is. So there's still 20 minutes left, which means that we have spent about 55 minutes. I would think that we should check, but I have literally had all my working erased. So I have nothing to check, and it'll be very boring for me to just repeat all the questions again. The thing also shows that I've done all the questions. So I'm just going to submit and take the risk of making some mistakes, and then we can talk about what those mistakes are. So let's see. So I made one mistake. I'm not very surprised I made one mistake. Let's see what that mistake is. And we also can look at 1 or 2 questions that were messed up. So that we were wondering if there's a nicer solution. Okay. That's interesting. It was 21. Okay, so what was going on for 21? Computationally, phi 6 times 5. Wait, what was that again? Was phi 6 to the 4 not enough? That's weird. So no, the good thing is that we have exactly the same workings, right? I just need to figure out what's going on. Oh, okay, I see. So you are guaranteed, right? So I didn't read very carefully. The question said, you know this and you want to guarantee that you have more than a 50% chance, right? Which means that I should not be using phi 6 because you don't know the probability. It's not that you know the probability and then you guarantee. You want to guarantee it before you know the probability. Okay, so that's my mistake. You are supposed to guarantee it by first checking that for 6 sevens is enough. So 6 sevens, we say we need 5. And the point is that you need to apply that 5 to the 5/6 as well. Okay. Now, this is the kind of reading error that does happen, and this is the sort of thing that you want to check, right? So it's a good teaching example. I suppose I'm also just curious about one or two of the others in terms of efficiency. There is no guarantee that AMCs have efficient solutions, but we just want to see. Okay, they use the recurrence. Okay, so that makes sense. I don't feel like it's very necessary, but it makes sense that you just look at combinations of blue and red marbles first, and then think about inserting the green marble or not inserting the green marble. So it's like if you insert the green marble, how many places can you insert it into? And then if you don't insert it, it's just follow this. So it makes sense. However, I don't think it's a huge time savings because it's only 6. And if it were very big, then this method would also take quite a long time. Okay, were there any other questions you're curious about? Let's just take a quick look. Yeah, I'm curious about the obtuse triangles one. Okay, so this is just a characterization, more carefully stating how it was done. It must include a corner and can only include opposite corners. Okay, so I think we're basically doing the same thing, right? I see this red and blue segment, which is effectively what we're doing. This last question. Okay, I think what we did earlier was a bit faster actually for that one. And then I'll just take a glance at the last few. Which works, exclamation. Okay, so it just means try it out and it works. This one, okay, so same thing, just pretty direct because take note of order again. This one, okay, direct counting and counting the complement. Yeah, I think that doesn't really make much difference. Roughly what we have done is the same, right? 1/3 times 12 times 1 plus 3 plus 3. Okay, so this is just a very colorful diagram to illustrate what we were saying earlier. And then this last one, kind of extension. Oh, okay, so I've got the first solution. The second solution is to use coordinates. Yes, it's a good idea to use coordinate geometry in general. Don't really need it here because this will require you to know the distance from a point to a line. But generally, do consider it as well. Okay, great. So that was the practice contest. As a whole, I would say that the questions are not really that wide ranging in difficulty as we normally expect for AMC10, but they are good practice questions in the AMC10 style. So I would say don't read too much into your score if you try this on your own, but that it is a good practice of the style of questions that comes out in the AMC10, especially if you haven't taken it before and you just want to have time practice on an online portal. So that's all I have to say. I may have another video for the AMC12 practice contest. We will see how that goes. But for now, that's all. So let me know if I have made any other verbal errors. I see I've only made one numerical error. Don't forget to like this video, subscribe for more Olympiad content. So thanks everyone, and bye for now.